Thank you. Good morning to everyone. It's a pleasure for me to be here today with you. And I will introduce myself briefly, very briefly. My name is Agata Fucile. I'm the WIVA owner, and I work on wireless sensor networks. Today, I will show you how wireless sensor network can play a key role in Industry 4.0 and how wireless sensor networks are related to machine-to-machine protocol and can take an important role and can be an important alliance for industrial application and IoT and industrial IoT. So let's talk about a brief introduction about Internet of Things. Internet of Things is a term that was introduced in 1999 by Kevin Ashton. It's a long time ago, don't you think? Yes? And Kevin Ashton used this term to describe a system where Internet connects the real world. Wow. In the last years, during the last year, this term has changed its meaning, of course. And people every day hears about IoT. But I think that common people doesn't really understand how IoT and industrial IoT can change our life, for example, during the next 10 years. What IoT means today? An heterogeneous kind of devices connected to Internet. And today there are several application fields like smart cities, connected mobility, health and fitness, wearables, smart home, smart agriculture, and industrial application. And today we will focus on our attention on industrial application. What are wireless sensor networks? Today, wireless sensor networks are considered the key enabler for IoT and industrial IoT. And we will see later why. A typical architecture for a wireless sensor network is a sensor field in which sensor node exchange data, perform sensing operation, and send data to a sink or base station, and the sink sends data to Internet. The user from a remote controller can access to that collected data. An important thing is that sensor nodes are self-powered, transmit wireless information, and are self-powered. More generally, we can say that sensor networks expand your ability to access data from the physical world. Sensor node. A sensor node is a very simple architecture. There are nodes that detect physical phenomena. Sensors send information to a CPU that do a basic processing, and then information is transmitted to a wireless transceiver. The advantages of wireless sensor networks are low installation cost and maintenance, because they are wireless, so there is a very low installation cost, and scalability and flexibility, and they are self-reconfigurable. For example, you have a new node to add to your WSN. the WSN detects the node automatically, and this gives a great scalability. You can move the node where you want, everywhere you want. And the network, the WSN, self-reconfigure. I propose you two IoT devices, a smartphone, for example, and a sensor node or MODS. They are IoT devices, but they are really different. A sensor node is resource constrained, and we talk about constrained networks for this reason. Let's see, for example, CPU, 4 megahertz for an 8-bit microcontroller for a sensor node. Or the memory is 4 kilobytes for a sensor node against 16 or 64 gigabytes. The battery life, I said that a sensor node is self-powered. So autonomy is an important feature to take into account. We want that a sensor node has an autonomy of at least 1 year, because we don't want to change batteries every 4 days or every week, for example. This make this IoT device very different from a smartphone, of course.
Can I ask a question?
Yes.
The price,
Sorry.
the price for the memory with 120 euros sounds very expensive. Why is that expensive?
Not so expensive if you think that we are talking about sensor node that as a transceiver CPU and sensor board for extension. We can have a sensor like GPS or MEMS, or so you can include a board of expansion, and sensor node must be of high quality. So you can't have an hardware of low quality. So this is this make increase the cost. Do you think this is a high cost? If you compare it with Arduino, I
guess there's you mentioned there's a microcontroller or even microprocessor.
Yes.
Depending on which one, the price goes higher. So, yeah.
Yes, but okay. Let's talk about WSN application fields. There are several application fields for WSN. There is environmental monitoring, air precision agriculture, or building automation, or industrial monitoring and automation. There are several advantages in using WSN in these applications fields. Let's see together an example of environmental monitoring. That is a Great Duck Island project in which an entire island was monitored. This is a clear example of how a WSN can extend and can cover great areas. And if you think that only 150 sensing nodes were used, these are very few nodes to cover an entire island. The second example is the famous ZebraNet that studied the behavior of zebras. In that case, the sensor nodes were collars attached to the zebras, and sensor nodes were moving and exchanging data. This is an example of how WSN can reconfigure. And third example is volcano monitoring in Ecuador. This is an example of how WSN and sensor node can be put in unreachable places. But what are we talking about? This is three projects that were developed in 2002 and 2004 for ZebraNet and Volcano monitoring. It's a long time ago. And they are three very famous projects. If you read the book about WSN, you surely find at least ZebraNet, but you can find that three very famous projects. And then I said to you that WSN are of interest for industrial IoT and IoT, but are we an ancient technology? What are the new features that have interest and an important role today? For example, these projects have had a problem, a very high packet loss rate. 50% is really a high percent. And the reliability of the network is one of the most important challenges in WSN networks. And examine the other challenges, the other important challenges. There is energy efficiency and the related network lifetime. The energy efficiency is very important if you think that the better autonomy have to reach 1 or 2 years. And network and data reliability. Network must have low latency, and we have to decrease latency. And we have to develop user-friendly HMI. But I think this is simple using Qt as developer framework. And for this reason, there are challenges to win. And for this reason, traditionally, industrial automation systems are wired. But now it's changing. Now the situation is changing, because we can develop M2M protocol. The new feature is that M2M protocol in WSN. This increase the reliability, for example. And we will see later how. And for that reason, WSN and M2M protocol have many advantages in industrial process, like automatic collection of data from a servers and non-accessible area, or flexibility of installing and upgrading the network, or decentralization of automation function. Okay? And several are the advantages in WSN. And there is another important aspect to consider. Consequently to that new features introduced, WSN and M2M protocols, market trends show a big interest about WSN. The forecast, for example, about global industrial WSN markets state that 440 million of internet-connected wireless sensing and actuating and tracking devices will be used in industrial and logistic and agricultural applications, for example. Or the most important strategic investment areas are wireless sensor networks and IoT platforms. And they are really, really of big interest today. Let's talk about machine-to-machine protocol. And let's see how WSN are related, and Qt can help we to develop M2M protocol in WSN. Machine-to-machine communication describe a mechanism and algorithms and technologies to enable network devices and service to exchange information without the explicit human intervention. This means that an heterogeneous kind of devices can be connected, and heterogeneous kind of data can be exchanged easily and in a very easily way. And for that reason, WSN are considered the key enabler for IoT, because they can develop M2M protocol. And I will present you two the most used and diffused M2M protocols: MQTT, developed by IBM, and CoAP, developed by IETF. CoAP is a constrained application protocol, and it was designed for constrained network. It's a very lightweight protocol. Is based on a REST paradigm, and is commonly used for web application. For that reason, is a HTTP compliant, and for that reason we can access a sensor node simply using our web browser and writing a CoAP address and find the node and access to the node. CoAP is based on stateless interactions. This means that when a client make a request to a server, the request must contain all the information about that request. And the server don't have to store any information, any additional information. And this improves scalability on networks. The other important feature is that the resources in a sensor node or in a node are identified by URI, Unified Resource Identifier, and this gives the possibility to access to a node, to a resource in a node. MQTT, that is message queuing telemetry transport, is based on a publish-subscribe architecture, and thus complies with REST architecture. Publish-subscribe architecture provides that there are publisher, there is a broker, and there are subscribers. Publisher has resources that are called topic. Publisher inform the broker that has that resource or that topic. Subscribers states their interest about a topic and make a subscription operation only once, and send a message to the broker telling that they are interested to be informed about that topic. Then, for example, publisher as a resource, publisher is a sensor node, okay? And sensor node, for example, as a resource that is a temperature sensor. And when the temperature changes, publisher sends a message to broker telling that an event is occurred and the temperature is changed. So, broker send to all subscribers a message informing that the temperature has changed. And broker is like the man in the middle. And we say that MQTT has intermediaries. And as you can see, this kind of architecture is one-to-many topic-based communication. This event-based architecture reduces the number of messages. This means that a better energy and with efficiency can be achieved with this kind of architecture. And it's different from a REST architecture that has a response and ask and response architecture, okay? The other important feature of MQTT is that the communication is asynchronous. This means that publisher and subscriber doesn't need to be simultaneously present in the network. And this gives the possibility to have a great scalability, because yes, publishers are publish their events and subscribers are interested, but they doesn't need to be all simultaneously present in the network. So, as you can understand, a node can move without inform other nodes about this moving, okay? And there is a version of MQTT that is developed for sensor networks that is MQTT-SN. This is a comparison between main features of MQTT and CoAP. The most important difference is that MQTT runs over TCP and CoAP runs over UDP transport layer. And for example, reliability mechanism has 3 quality of service for MQTT and 1 quality of service that is provided by confirmable messages for CoAP. And an important thing is that, yes, MQTT is a publish-subscribe architecture, but CoAP provides a request-response architecture, but may provide a publish-subscribe architecture, and we will see later how it can provide that. Okay, this is another comparison between these two M2M protocols. The header, for example, is higher in CoAP, 4 bytes, and 2 bytes for MQTT. But the number of message type is 4 for CoAP and 16 for MQTT. This means that when you have to write a firmware in a sensor node, you have to implement more code, and this may be a problem for your memory usage. Messages is asynchronous for MQTT, or synchronous and asynchronous for CoAP. Security in CoAP is provided by the TLS protocol, and for MQTT is not defined in the standard, but TLS of TCP can be used.
Just want to point out that the TCP header is bigger than UDP. So even though UDP is a smaller header, TCP is bigger.
No. For CoAP and QtDay is different.
I know, what I'm saying is TCP is bigger. So even though you're saying header for CoAP is bigger.
Yes.
If you add everything, CoAP is smaller.
He's talking about
If you,
transport layer either.
okay, if you had, sorry, I don't understand. If you had,
If you add the UDP header,
okay.
UDP is smaller than TCP.
Yes. Okay. These are the results of a real sensor network, and I propose you some useful comparison. For example, between packet loss and delay, and this comparison is done when configurable message reliability method is provided by CoAP, and QoS level 1 reliability method is provided in MQTT to be this comparison more consistent. And we find that when packet loss increases, CoAP provide a lower delay, and when the packet loss decrease, there is a lower delay for MQTT, and this is due, of course, to a number of retransmissions. The overhead, for example, is interesting because when we have a network with a high loss, CoAP overhead is less than MQTT overhead. But when the packet loss is high, then for small packets, CoAP has still less overhead than MQTT, while for big packets, CoAP has a higher overhead than MQTT. And memory usage is less in CoAP than MQTT, and the energy efficiency in CoAP is higher than MQTT implementation. Okay, Qt has APIs for both MQTT and CoAP, Qt MQTT and Qt CoAP. And actually, Qt MQTT is included in Qt for Automation, or there is a GPL version 3 license, while Qt CoAP will be included in Qt for Automation 5.13. And the two protocols provide a client implementation for Qt MQTT, a level 5 support for authentication or error handling, while for Qt CoAP there is a request response architecture, but Qt CoAP provides discover and observe functionalities that make possible to develop to add the publish subscribe implementation. As you can see, CoAP payload is as a text format, but JSON, XML, or CBOR formats. These are code examples about Qt MQTT, and as you can see, we can use only two classes to implement a client in MQTT: QMQTT client and QMQTT topic name. We can declare a client of kind MQTT client and set the host name and set port, default port, and make simply a connect where a message is received. And as you can see, the slot is a Lambda function, and the capture list is a message and the topic name. And for example, we can print the topic name or the message content very easily, and these are a few lines of code. The subscription request can be done implementing a slot and use the method subscribe and do something. If subscription is not successful, we print on screen, is an invalid subscription. So for the subscription operation is only a method call, nothing else. It's very easy, very simple. For example, Qt CoAP, the client version can be implemented by Qt CoAP client, Qt CoAP request, and Qt CoAP reply. We declare a client of kind Qt CoAP client and make the same connect when the signal is emitted, signal finished is emitted. We can write our slot on finished and detect this signal. And for get and put operation, we can use methods simply get and put. As you can see, get as the URI, the resource name of CoAP, that is simply an URL in which there is the sensor node, IPv6 in this case, and the URI name. For the when we do a get, we are asking to the sensor node to send the information about that resource or that URI. And when we do a put request, we are asking to sensor node, we are sending to sensor node a payload with information, and we can change the value on our URI resource of that sensor node. We can do the same simply declaring a reply of type QCoAP reply and using the method get with URL and make a connect where sender is reply, the signal is finished, and we can implement our slot to receive our message. Discover operation are a particular type, particular kind of GET requests. But they are done with using a particular URI, a particular URL, sorry, that is CoAP, sensor node address, and well-known core. This sends back a message with the resource list. This means that if a sensor node has a temperature and humidity sensor and LEDs, for example, you can know what resources are present in that node. The discover operation can be done in the second example by a reply, and it's very simple. We have the method discover, and we make simply a connect, and the signal is discovered, and we develop our slot on discovered. The example is an example of an observation request. When we do an observation request, we do something that is just like the publish-subscribe architecture. We are saying that we are interested in a server notification about a resource. And when a sensor node want to be informed about a change, there is the signal notified, and we can declare request of kind QCoAP request, and we have the method. We use the method of observe, passing a parameter, the request as parameter, and we do a connect, the same connect, signal notified and slot unnotified. When a node isn't interested to be informed about resource changes, the client can ask to be cancelled by using the method cancel observe. Well, there are several advantages in using these two protocol and QtCoAP and MQTT. We have the possibility to develop easily and with a time to market very low because they have APIs that are very easy to use, as we saw, and there is a lower time for implementation. You can find a long-term support for that API. As you know, Qt do this advantage. And there is the bug support, for example, and Qt CoAP supports DTLS. As you can see, there are third-party libraries implementation and that are libcoap written in C and Mosquito for MQTT written in C++. But they, for example, libcoap doesn't provide the security protocol that is the TLS, while Qt CoAP supports it. And for example, Qt MQTT supports level 5 of authentication of a security level. So, as you can understand, the use of these two APIs make really easy to develop application based on IoT and M2M protocol, and we can easily integrate them in sensor node. Okay.
Any question? Oh, sorry, I don't have wireless microphone, so I have to ask. Please. No, no wireless.
Only one question from my side is, if we talk about the content of the packet, let's say, I have a sensor of temperature, of pressure, or whatever. Is there any specification on how the information on temperature should be supplied inside an CoAP or MQTT? So if I buy a sensor, a pressure sensor from supplier number 1 and supplier number 2, both of them supports CoAP, and is there any specification on how the content of the message should be formatted, or no? Is completely supplier dependent, vendor dependent?
Doesn't matter what kind of sensor you have. The MQTT and CoAP are application layer protocols, so this is independent from the sensor that you use. So you can have every kind of sensor. If you have an hardware that provides a sensor board with the sensor, you need only to connect a sensor to your board, okay? But M2M protocol manage the difference between one sensor and another independently. It doesn't depend on what kind of sensor you use, okay? This is application layer protocol, so you have the necessity. You don't need to interface with that kind of sensor. You can have every kind of sensor, because M2M protocol give you an application layer that make your sensor node like an address, okay? So you use this URL to identify the nodes, and the URI name that is that resource. So you can't you don't need to think about what sensor you have in your board.
But if the temperature is in degrees Fahrenheit, it's up to the sensor.
Sorry?
If you have an address, let's say for a temperature value,
Yes.
the unit of measure that
You can choose it. You.
sensor dependent.
Yes, but you.
There are standards. But you can choose your standards. There are standards. So some devices will follow some standards. But it's not a requirement.
Okay.
I know that in MQTT there is a role of a server to intermediate all sensors. In CoAP protocol, there is a role for notification, I see, but to coordinate, there is a server or not? It's completely asynchronous.
CoAP has an architecture, RESTful architecture that is a client-server architecture. So you have the clients and the server. The clients do a query, okay, a request to the server, and the server asks to that request. This is the basic.
Standard server CoAP.
Well, I explain you what I mean. You can implement the server in a WSN, and the server can be an element of your WSN. For example, the sink or the base station, okay? You have to think about the base station or the sink that collects data as a server, and all sensor nodes that are client devices, okay?
Any question? Now that I have a wireless microphone now. Okay, thank you again, Agata.
Thank you.